All right, is everybody ready?
Yeah, I think we're good.
Okay. All right, so we're going to talk about raster data analysis today. This is the last week that we will be kind of introducing new ideas, new concepts for GIS. We'll have two chapters related to raster data. So the first one is chapter 6 in the book, and I've got an assignment up for that, and then we'll do one last tutorial in the book for kind of more applied raster analysis. So we're going to do a little bit of that today. I'm going to do an introduction to what raster data is, how we use it, and then we'll use ArcGIS to explore properties of raster data and do some basic analyses with it. So hopefully we'll have enough time to do this walkthrough together at the end of class. All right, let's get into talking about vector data. I borrowed some slides from Dr. Stephen Taylor in Western Oregon University, as well as the textbook, some of the figures. All right, so we've talked about raster data. We've got a kind of general understanding of what it is. It's gridded data. Basically, it's a matrix, and the matrix has defined spatial bounds. So we think about a matrix has rows and columns. You can think about it as an X and Y axis. And although we kind of draw it as a grid and we visualize it as a grid, it's really just points, right? It's just a point with a coordinate associated with it. And that point also has a value. So here's a table. It's kind of like a summary table for this raster, and it says, okay, this is a categorical raster, right? So it's got different categories or numbers assigned to a cell. And then this is just kind of summarizing it up. We have this many cells with this value, and we have some sort of descriptor associated with that category. We're going to be talking a lot about digital elevation models in class. I think those are most pertinent to a lot of civil engineering applications. So a digital elevation model, also a DEM, that's continuous data. And that just means that instead of categories, the data could take on any value with decimal points. So an infinite number of categories, basically. There's different kinds of continuous data rasters. I'm showing another one here. This is a precipitation map for the US, average annual precipitation. So we can kind of think of these, we visualize them as flat, right? There's just a cell, it's got a center point, and that center point has this value attached to it. But you could also visualize those three-dimensionally. So here's just a look at, say these are elevation values at the center point. We could visualize that so that it actually looks like a surface if you connect all those points. The value applies to the whole cell. And so that's when resolution becomes important. So if this is 10 by 10 meters, that whole 10 by 10 meters has a value of 40. But if it's 100 by 100 meters, you know, that's a coarser resolution. The way rasters work in georeferencing is that you've got just the table or the matrix that has all the raster values in it. And then we basically define the XY location of a corner. So if we know the XY location of a corner of a raster, we know how big a grid cell is, and then we can spit out the data and then plot it. So there's not much when it comes to georeferencing. It's really just an XY location, a projection, the pixel size, and then the data itself. All right, I love rasters. I think they're beautiful, especially when it comes to visualizing the Earth. This is a digital elevation model of a river in Washington State. This guy, Daniel Coe, he's a geologist, and he really does some cool stuff. We'll look into his work a little bit more later, but he does some really cool visualization stuff with rasters, and especially high resolution digital elevation models from LiDAR data. This is a digital elevation model. It's just showing, you know, the probably darker is higher elevation values and later is lower elevation values as we kind of move downstream. This is the same river system. It's now a relative elevation model where the bottom of the channel is 0 and everything kind of moving out and away from that is all relative, is some elevation value relative to the bottom of the channel. So if you were to trace a line down this, you would see that it slopes downstream. If you were following kind of that main channel, you would see that it slopes downstream. If you were to do that same line on this main channel, it would actually be totally flat. So you've kind of taken the tilt out of the raster here. And we'll actually look at relative elevation models a little bit later. Here's a LiDAR data high resolution of the San Juan Mountains just north of Telluride. And so you can kind of see a lot of cool stuff happening here. Glacial movements and carving. I kind of love exploring the mountains when it comes to this stuff. All right. We've talked about categorical data. Here's just another look at what that data is, what the data are. We've really important raster, which has been generated from satellite data, land use data, and it's been categorized as, in this case, built up or urban, which is red, cropland, and then everything else has been lumped together in gray. So cropland, urban, and then, forests and fields and other things like that. Here's just a comparison from 2005 to 2011, and then 2005 to 2016. So you kind of see urbanization, you can see kind of like the highways being built around the city. I don't actually remember what city this is, but we'll say it's Dallas or something like that in Texas, some big city. This data is actually used, if you're in my hydrology class, this is data that's used for stream stats, and this data is used to calculate kind of runoff coefficients for watersheds. Here's another, our continuous data sets, annual precipitation in inches. There's not categories here, although it's visualized kind of categorically, right? We have these bins that we use to kind of cut off the classes, but you click on any one of these cells and you can have a decimal, for example, 20.1256 inches of precipitation in a year. Resolution is a really important aspect of raster data. We've been dealing with vector data so far, and vector data doesn't really have a resolution. We talked about map scale or data scale, the fact that ultimately these vector data have been digitized based on some sort of map or something like that, or GPS data, for example. They do have an actual kind of inherent or embedded resolution in terms of the decimal point accuracy of the data, but you could zoom in forever on a vector. There's no grid. You're not going to come up with some kind of resolution limit, but raster data does. And here's just looking at, if we started with a polygon that's kind of perfectly smooth, we could sample it as a raster. You can convert polygons or lines or points into rasters, and this is sampled by a 1x1 meter cell grid. But then you can make that coarser and coarser, and that representation becomes kind of less accurate and less precise. Why do we have different resolutions? Well, raster data is really has really big data files. You can think of we'll look at a grid for Colorado, and it's going to have thousands and tens of thousands of grid cells in it. So the data space can be really big for rasters. So we might not need a 1x1 meter cell if we can do 80 by or 4x4 meter cell, for example. This image here, you can see 30-meter resolution all the way to 3-meter resolution, and this is a digital elevation model, a hillshade, kind of showing it three-dimensionally if the sun were to shine on this. And you can obviously see that you lose a lot of information as you have a coarser raster. But we might not need this resolution if we're looking at the whole state, for example. 30-meter might be good enough. Rasters can have bands, and bands are basically layers or sandwiches of rasters. And we think of bands often with visual data or color data. if we were to have, for example, a red, a green, and a blue band, those could be represented either by color or just by black and white, because it's just 1 to 255 is usually the color range that we have for color data or imagery data. And if you put those all together, you can actually end up with a red, green, blue composite image. So if this color image in kind of natural light color is actually comprised of 3 bands or 3 rasters that overlay each other. And those 3 rasters have the information that we need for to represent red, green, and blue. And this is kind of a simplification of the visual color spectrum. So if you see the electromagnetic spectrum in the visual range, it goes from purple all the way to red, or violet all the way to red. If you just sample the image in these 3 areas, you can kind of get enough information to visually represent the image, but it's not complete data. So bands are layers in a raster, and a raster can have many bands within it kind of sandwiched together, one raster file. Here's just a look at raster coordinates. So it's going to be pretty similar to what we've been dealing with. You need a projection, right, and a datum. Although the additional information we have is the resolution of the grid cells. And so if we look at the source data, it's going to have the cell size in it. Here's a look at what the projection file kind of looks like. Sorry, this is the file that kind of tells you the information you need about the raster. So a raster will have a projection file, and it also, in this case, this is a TIFF image, raster image. This also has a TIFF world file, .tfw. And that TIFF world file has just some basic data in it. The first is the grid cell size. In this case, it's in units of degrees. And then it's got the origin of that corner, which is typically the northwest corner. These, so the second and third rows are rotational components, usually set to 0 if the image isn't rotated. We talked about visually representing vector data, and you spent some time doing that. Raster data has its own kind of set of visualization techniques, and you'll play around with that in the tutorial. The kind of default one is stretched, and so if you get a raster, and in this case it has values between 15 and 4,385, it's just going to visualize it as this kind of stretched or continuous color spectrum or color map. And you could change that color map from black to white or red to blue or anything in between. Red, green, blue composite is usually what we use for aerial imagery or images. We could have classified, which is what this relative elevation model is shown as. And so we just kind of bin the data in certain ways and just assign values of color to those different bins. And then we could also have unique categories, which in this case, you just pick a color to represent a particular categorical value. One way that raster data is handled is with pyramids. Pyramids are basically different rasters with different resolutions that are sandwiched together in a file. What it means is this allows you to visualize the data or display it more quickly. So if you're zoomed really far out on this raster image, then ArcGIS is not going to try to draw a million little pixels. Rather, it would draw this kind of coarser resolution one, just for visualization. As you zoom in, it's going to show you a finer and finer resolution raster. So you can build pyramids in ArcGIS. Sometimes it does it on the fly. Sometimes you can just make it happen. It'll create a new file. So it'll add the storage size of the raster by about half, but it'll make it much easier to kind of navigate and visualize the raster. resampling. So this pyramid is kind of like, you end up to build this kind of pyramid file, you end up resampling the raster. So if this is your highest resolution version, you resample to kind of get coarser and coarser resolution. So there's different schemes and ways to resample a raster, and it comes up in a couple things. One is so we'll just kind of visualize it. If we go from fine to coarse resolution, we have this kind of fine resolution raster here on the left. If we want to resample to make a coarser resolution raster, you could put that coarser grid over it. And then there's different techniques, maybe averaging, something like that, that would allow you to get a new value for this coarser resolution raster, which is a composite or a resample of a bunch of different values within that coarser grid cell. So rule must be chosen to do that, and we've got different rules that I'll talk about in a second. So block resampling is how we get pyramids. We basically just take an average of values within the new coarser grid cell, or it could be a minimum, mean, maximum. There's, you could do different things depending on what you want. There's other techniques. So nearest neighbor resampling, what it does is if you put this coarser grid over the raster, it's going to find the nearest neighbor, or the value. It's going to take the value of the raster that's kind of most complete, or the cell that's most completely within the new coarser cell. So it's going to basically just take a point, take a sample, whatever the value of the raster is underneath that, it'll apply that to the coarser cell. So it is important for categorical data because it doesn't change the value. You could imagine that you have, so categorical data, and if you did some average and you had like a cell value of 1 here and 2 here, then maybe you would get like 1.5. Well, that doesn't work for categorical data. We don't want 1.5, so we just want to maintain those categories. So we use nearest neighbor resampling only for categorical data. There's other methods there's a method called bilinear, there's a method called cubic convolution. We don't need to know what those mean, but we need to know that they are applied for continuous data. And so if I have a digital elevation model, for example, with continuous data, I want to use one of these techniques. I don't want to use nearest neighbor. Resampling is also required when we project rasters. So projecting rasters, you're going to basically change the coordinate system, and you end up resampling the raster for that. So it's really important that we choose the right technique to resample the raster when we reproject a raster. Reprojecting a raster degrades the precision and accuracy of it, so we want to minimize the amount of times we do that. And there's a different tool for projecting rasters. The project tool is just for vector data. The project raster tool is for rasters. So you put in your input raster, you give a name for the new projection that you're going to do for the new raster file, and then you can choose the resampling technique. That's this nearest neighbor has been chosen. That's fine for the this is an aerial imagery file, but it's not okay for digital elevation models, which we'll look at in a minute. Any questions so far before I start talking a little bit more about digital elevation models? Okay. So digital elevation models, or DEMs, I'll call them DEMs from here on out, are rasters that show us topographic data. And each cell value, the midpoint of that, is assigned an elevation. Here's a digital elevation model with a line that's been drawn across it. And we sampled the elevation across this line, this profile. And so what you can see is an area where we have kind of a peak right here. The darker values are lower values. And so you kind of see valleys and peaks as you sample across this digital elevation model. There's a lot of different information we can get from digital elevation models. The first most basic one is a hillshade, and this is just a visual representation of it. It basically shines an artificial sun on the digital elevation model and creates kind of shadows, so you can kind of see the textures and and kind of easily, or it's easy for the eye to kind of interpret the topography. We can look at aspect. Does anyone know what aspect is? What it means? What aspect means is the direction that the pixel is facing. And so in this case, we've assigned different values or colors to, for example, northeast facing slopes versus south west facing slopes. So aspect is important because we care about if we want to know how much sun pixel gets, if we want to know, for example, for snow hydrology, aspects are really important because more snow sticks around on kind of northern facing slopes as opposed to southern facing slopes. We can make a slope map. This would be important if we wanted to identify, like in a county, slopes that were really steep that we might not want to develop on. And then here's just an elevation map with colors associated with different elevations. Here's an application of digital elevation models of rivers. You guys are going to get a lot of river applications from me. What we see here are two aerial images of the North Fork of the St. Vrain River. It goes into Lyons, Colorado, in the Front Range in Boulder County. And these aerial images span before and after the 2013 flood. So here's a river before the big flood that they had in 2013. And then here's what happened. The river moved quite a bit, changed sides of the valleys. There's a house that had a driveway and it connected to a highway that got cut off from the highway. I think they have a bridge there now. The house is still there. And what I am showing is a line across this digital elevation model that's so you see some colors that represents the elevation, and it's superimposed over a hillshade image. So you can kind of see the texture as well, the topography. And I did that same line for the pre-flood digital elevation model and the post-flood. And so that's what these cross sections look like. So pre-flood is solid black, and then post-flood is dashed lines. And what you can see is where this line is, there's kind of a relic channel, a channel that was there historically that's been kind of plowed over by this development, roads and stuff like that. That's actually the area that the channel reoccupied. So there's that relic channel. And then here's where the channel actually, carved a new channel out as a result of the flood. And it filled the original channel from pre-flood, it filled that channel in. So the application here is that you could identify areas that might be more susceptible to what's called an avulsion, where the channel finds a new path through the floodplain based on the topography of the land prior to the flood happening. Hillshade images, like I said, are ways to visualize digital elevation models. There's a tool that will allow you to create a hillshade. And it's basically a hypothetical illumination of a surface. And so the hillshade tool allows you to specify the azimuth or degrees along a compass that the sun is shining on. So the default is northwest, as well as the altitude of the sun. The default's 45 degrees. And so you can create different hillshade images that will be kind of like either, midday or afternoon versus like sunset kind of a hillshade. The defaults usually work pretty well, but you could change that to visualize it a little bit differently if you wanted to. I've talked about relative elevation models. They're really useful for interpreting topographic features along a river. And it's basically a D-trended DEM. So to create a relative elevation model, I would trace a polyline across the profile of the bottom of the stream, and that'll sample the elevation along that stream, and then I can use either cross sections or some other tools to basically subtract out that slope and then flatten out the elevation model. So it gives you a raster that says now the values are the height above the river bottom as opposed to the absolute elevation. Another thing we'll do a lab in class later is a DEM of difference, it's a DOD. And what this can show us is how land changes over time. Here's a river example. where we have areas blue is where the river filled in, and red is where the river carved out and eroded sediment. And you just subtract the kind of later DM by the earlier DM to create this digital DM of difference. We could imagine using this for construction sites or mines or something like that, where we want to track volume changes over time. And if you're thinking about kind of a grading plan, you could create just 2 different DMs and look at your cut fill differences. We use Raster Calculators to do this kind of analysis. And there's a lot of different functions you could use. You could, for this example, the Raster Calculator is simply just a subtraction calculation. You could do addition, you could do functions like slope, for example, and we'll get to use Raster Calculator in these tutorials later. So if you want to read more about raster data, we've got chapter 6. We also have this link which gives you kind of a brief overview of raster data, and I'll post these slides for that link on Canvas. Great, so let me know if you guys have any questions. And if not, we can go into our raster analysis exercise.